Today is 4-4, choosing a simple random sample. So, like, here's like a little scenario here of how to do a nice little random sample. Look how cool this chick is here. Each day in class, Miss Herbert randomly selects 5 students to present homework problems on a whiteboard. To make this selection, like, she uses a set of craft sticks with each student name written on the stick. She puts the sticks in her cowboy hat, mixes them well, and pulls out 5 sticks. Like, how awesome is that? That they just didn't even say a hat. It had to be a cowboy hat. So the students' names that are on the 5 sticks are selected and present the homework problems. That's just a simple random sample. Put all your names in a hat and, like, pull them out. Everybody's, like, name was on an equal size stick. That's one way to do a simple random sample. So to define the things right here for our worksheet, a simple random sample, they usually call it SRS. You're going to see that abbreviated a lot, like simple random sample, is a sample chosen in such a way that every group of N individuals, N is just like the number of people in the population, so every group of N individuals has an equal chance to be selected in that sample. So that's a simple random sample, and then we might as well define sampling variability since we're right here, is the fact that different random samples of the same size from the same population, produce different estimates. So there'll be some variability in the samples. That's called sampling variability, and we'll see that when we dive into some questions today. It's a pretty basic day until we get to the end. And then it's just like kind of head scratching. It's like, say, what now? You know, like honestly, I think some of it feels a little backwards the first couple times you learn it, and then the more you do it, the more it starts making sense. So, all right, so check it out. There's a couple of ways to do it. So here's what we got on the first one. When landfills run out of room, they are sometimes converted into parks. Does the presence of a landfill underneath affect the trees that grow in the park? So one such park has 283 trees, and researchers want to closely inspect a sample of just 20 trees. Describe how to select a simple random sample of 20 trees using slips of paper. So, all right, this is pretty lame to do it slips of paper-wise in the world that we live in, but you can do it, and your homework asks a lot of it. Give each tree a distinct label from 1 to 283. Right? Aren't there 283 trees total, right? So you're just going to number all the trees, you know, like 1 to 283. Number 283 identically sized slips of paper, right, from 1 to 283. So every slip of paper is identical. You put them into a hat and mix well. And then since you're only testing for 20 trees, you're going to select 20 slips of paper and inspect the 20 trees that are numbered. Doesn't that sound tedious, though, to do that? Like, if you wanted to, like, totally pick 20 random trees out there using slips of paper, you'd have to get 283 slips equally the same. What a waste of time. Another way to do it is with a random number generator. You've even seen me use some random number generators in here. The computer does it all. So what you do is, if you use a random number generator, you give each tree a distinct label from 1 to 283, like you're still labeling all the trees. Randomly generate 20 integers from 1 to 283, but the problem with random number generators is it will have repeats, like it'll repeat sometimes, so then inspect the 20 trees. So let me show you that. That's how simple it is with this random number generator. I just have to number all my trees. You'd go and do that, and then I'd have 1 to 283, and then I'd do that 20 times. All right, tree 142, we're going to expect you. Tree 79, tree 225, and et cetera, right? You know, like you would totally just do that. If you get any repeat guys, you just ignore it and try again in that situation. But wouldn't that be so much faster than making all those slips of paper in that case? So slips of paper is kind of silly. It's easy for small things. Like if we want to do that with us, you know, we're a small group, it would make sense. So, all right. Question 2. A safety engineer at an automobile assembly plant knows that 180 pickup trucks will be assembled tomorrow. To meet federal regulations, the engineer must select 5 of those vehicles for safety testing. I will let you and a neighbor try to fill out these blanks. You know, there's 180 total pickup trucks, and they want to select 5 of them. Using slips of paper, give this guy a shot. I'm going to pause the video here real quick. So let's see how we did. Give each truck a distinct label from 1 to 180, right? Isn't that the total number of trucks in that case? Number 180, identically slips of paper from 1 to 180. Put these papers in a hat and mix well, and how many should we select? Select how many slips of paper? 5 slips of paper, and test the 5 trucks. It's pretty basic. You've been doing things like this for years in classrooms where they randomly select students by putting names in hats, and sometimes they have the wheel where they spin the wheel with your name on it, you know, and all that stuff. So pretty neat. So, all right. What if we wanted to do it with a random number generator? Give each truck a distinct label from what to what? 1 to 180, right? There's 180. Randomly generate 5 integers from 1 to 180. Ignoring repeated integers. Test the 5 trucks that are labeled with the generated integers to see if they meet federal regulations. So that's a nice random sample in that case, taking all the bias out of it. You feel okay with those 2 examples about random samples? So, all right. And then there's sampling variability. You remember a couple of days ago we read those words from the Federalist Papers, and like we picked like 5 words at random or whatever, and or it wasn't even at random. You just picked 5 words. When you did it by yourself, a lot of people had some bias in what they picked because it's like, oh, I picked nothing but big words, or I picked nothing but small words kind of stuff. You didn't randomly do it. And then here, when they did it randomly by picking words, the dots were much closer together. If we keep doing that over and over and over again, this sample would not always look the same. There would be some variability. So there is some variability with sampling variability. We defined it earlier, and what it is just like if you keep taking random samples of the same size from the same population, you're going to get different estimates. So here we go. Here's our first example of sampling variability. The median household income of a random sample of 371 Virginia households is 68 grand plus. Do you think that the median income of all Virginia households is equal to that? Like, should this number right here be the exact true median? What do you think, yes or no? They randomly sampled 371 households in Virginia. Is that an accurate enough thing to say? Yes, sir, Bob, that is the true median of all Virginia households. Yes or no? No way. It is not. Because different random samples will produce different medians. Like if you did that again with 371 different households, you would get a different answer most likely. You know what I mean? It would be close, but it would be different. It is unlikely that this sample provides a median that is exactly correct. So that sample has 371 households in it. What do you think would happen if they increased the sample to 1,000 households, which is more, right? You know, it's like 3 times as much in that situation. Do you think the estimate should be more or less likely to be close to the true median? What do you think, more or less likely? The more people you sample, what do you think, the more accurate or the less accurate? It would be more accurate to the median income, the true median. Like you would have to sample everybody. You would have to ask every single household in Virginia to get the true median. But there's no way that that's like humanly possible. You know, it's just like way too hard to do. So the more people they ask, the more likely it is. So, and then let's fill out this chart. Using a larger sample reduces the sampling variability. So the more people you ask, the less it's going to vary. In other words, the estimates become closer to the truth. But be careful, increasing sample size does not reduce the bias. Like if we go back to those push-up questions that we did from lesson 4.2, if I said, hey, come on down and sign up for the push-up contest, even if you got more volunteers, it doesn't mean that the bias has gone away because the people who are good at push-ups would just probably show up. Like there'd just be more of them. Or, hey, do you wash your hands after using a public restroom? Even if you asked more people, it doesn't stop them from lying about it, you know? So it doesn't reduce the bias. So, cool. That's, I think, pretty basic. I think we get that.